So hello everyone, welcome back. Now let us start problem number 15, which says a thick spherical shell, inner radius A, outer radius B, is made up of dielectric material with a frozen in polarization with polarization is equal to K upon R in the direction of R cap. K is constant, R is the distance from center, and there is no free charge. Alright. The electric field in all regions, find the electric field in all regions by two different methods. Alright. So one is by using, I think, Gauss law, another using by, yes, so one is by using we need to locate the bound charge, and then using Gauss law we need to find the electric field, and other is we need to find D and then E. All right, using this method we will get our answer in just few seconds only. So before starting this question, I suggest you to read from section number 3 up to here. All right, so it will be more easier for you to understand. All right, now let us start. So this is problem number 15 on page number 183. Yes, so we have a similar problem as a spherical shell and inner radius A and outer radius as B, and polarization is in this region. All right, in this region from inner radius to outer radius. So first of all, here is a word frozen in polarization, which means that it is like permanently polarized. All right, so the word frozen in polarization means the polarization is frozen in that area and it will be permanent in that area. All right, in that spherical area. So if polarization is here, then here it will be positive sign, oh sorry, here will be positive sign and here will be negative sign on this area. All right, inner area, and here will be positive, because we know that positive to negative the polarization goes, same as the electrons, negative to positive. Sorry, I spelled I said it wrong, from negative to positive. All right, so we need to find the electric field now. So now let us start. We need to first of all find the bound charges. Rho b is minus del dot p, and sigma b is p dot n cap or r cap in this case. So rho b is p dot minus del dot p. So p here is k upon, that is small k upon r in the direction of r cap. All right, so these are in spherical coordinates, so we have to write in spherical coordinates. So we have 1 upon r square del by del r square k upon r. I am writing directly. I have discussed about spherical coordinates in our previous videos. I hope you have learned till now. So we get k upon k into r, and with the derivative k upon r square with a negative sign, negative due to this. So rho is this rho b. All right, now sigma b, p for outer area. So let me just write it in two parts. So it will be k upon inner area is a, and with a negative sign for r less than a, and k upon r for r greater than a. All right, I hope you let me just shift the page a little bit. I hope you got how we write it. All right, so polarization in direction in area greater than a. If you are talking about this area, then you can write b here, or if you are talking about whole space, if suppose r is here, then we are talking, or you can write, if it is equal to r is equal to b, then you can write k upon b here, or you can write k upon b. if R is equal to B. All right, and if R is greater than less than equal to A, it will be this case plus. All right, so we have found out sigma B and rho B bound charges for the inner and outer area. Now let us use Gauss law and find the electric field. So using Gauss law, we know that for spherical Gauss law, we know that for spherical E is given as K Q enclosed upon R square. We know that, all right, in direction of R cap. So as charge is not here in this region, so electric field will be 0 because Q enclosed is 0 in region R less than A. Q enclosed is 0, so E is 0. Now in R greater than A and less than B, in this case we need to simplify for Q enclosed first of all, because as we are talking the concept of polarization, so we'll use the formula rho B d tau plus sigma B dA. All right, so rho B is K upon B plus d tau is so rho B is K upon R square, and d tau as we very well know for spherical symmetry 4 pi R square dr. All right, so on the, with a sign of integration, and similarly dA is for spherical symmetry, dA is 4 pi a square, and sigma B we just calculated for less than or less than equal to A, that minus K by A. So this will be the Q enclosed in this case. So let us simplify. We get KR into 4 pi, and the limits, first of all, limits will be from as the polarization is from this area up to increasing from this area to R. Suppose we are letting a small strip at a distance R. Okay, so from A to R, the volume will be volume charge density will be from A to R. So we get 4 pi R minus A plus K into 4 pi, and with a and with a negative sign here. All right, so on simplifying we get 4 pi K and with a R and with a yes. All right, so we get 4 pi K into R square, and here Q enclosed was, and rho B was negative, so negative in this, and we get a negative here. All right, so Q enclosed we got 4 pi KR, and so E is equal to K into, this K is different, and let me just give it a capital K, 4 pi K small k upon R, and we get K upon, cancelling the terms, let me just cancelling the terms, this 4 pi epsilon naught, only epsilon naught will be left, and with a negative sign, epsilon naught R with a negative sign. So this will be the electric field in the region A less than A and greater than B. Now this will be the region. Now let us talk about the region R greater than B. All right, so for R greater than B, we have we did a problem 4.14 that if charges are a bit if charges we move charges a bit, then the total charge remains 0. We did it in problem number 4.41 on page number 179, and we proved that bound charges becomes 0 there. All right, total bound charges vanishes. So why I am talking about total bound charges, because we are talking about the case, suppose here outside the spherical shell, which means now from the rho b and sigma b both will be considered, and they both will get vanished out. All right, we'll not talk about limit here. All right, we'll simply talk about the area outside. So the only the volume and on the surface will be considered, and they will vanish out. We read it in problem number 14, on page number 179. So directly we can write, as q enclosed is 0 proved in previous problems, E will also become 0. Let me just show you how where we have proved it. Let me just a second. So this was the problem we proved, that we took q enclosed as this, and we proved that q enclosed the total charge vanishes. All right, so I hope you remember that. Now this was the first method, calculating electric field by first method. Now let us go to the second method. So method number 2, which says or B part, you find D. All right, so D is from equation number 21. D is epsilon naught E plus P. You very well know if you have read the theory, or you can read it. So D is this one. So as free charge, and after in problem in equation number 23, we found that integration over closed integral d dot dA is equal to q free, and q free in this case is 0, so d will be 0. So we have found out, let me just focus, yes, so d in this case is 0, so E will be minus p upon epsilon naught, simply from this equation. All right, so E you can write minus k upon epsilon naught r. So in just few seconds we found out in the direction of r cap, sorry, electric field. So I hope you got the idea of bound charges and electric displacement, and how we use them in problems. So that's all for this video. See you in next video. Bye bye.